Okay, now we're going to look at column space. So if you're trying to find a basis for the column space of a matrix, there are two different techniques you can use, and we're going to look at both of them. The first one is the first one is just to realize the transpose. If you've got the matrix A and you want its column space, that's the same thing as the row space of A transpose. So what we can do here is to find a basis of the column space of this guy. This is the same matrix we had before. What we can do is just take that matrix. I called it M before. There it is. If we want its column space, I can just take its transpose of M, and then just row reduce that. And it gives us this. So let's see, that's over here. I'm going to say this is A, and A transpose, when we take the RREF, that top row becomes 1, 0, -3, -3, 0, 1, 1, 2, and then 3 rows of zeros. So what it did, it went through and it sort of sifted out all the rows of the transpose that were linear combinations of the other, and it just leaves us with those. So our basis is just, now I'm going to write these as column vectors because we're talking about a basis of the column space of this original guy here. So that's going to be 1, 0, -3, -3, and 0, 1, 1, 2. And that's our answer. Okay, the second method is this. What you do is, instead of taking the transpose, you take the original matrix A and row reduce it. And when you row reduce it, that's going to it's going to leave you with leading ones. You mark those columns that have leading ones. Those columns are going to be linearly independent. And so then you go from there and you look at the columns in the original matrix that correspond to the columns in the reduced row echelon form with leading ones, and those give you a basis of the row space. So let's look at that. This is actually, that description makes it sound complicated, but it's actually pretty easy. You just take the matrix M, you row reduce it. Now when I row reduce this, I'm going to copy this whole thing down. 1, 0, 1/3, 2/3, 1, and 0, 1, 1/9, 2/9, -1/3, and then 2 rows of all zeros. Once you've got that, you just look over here and you say, here's a leading one and here's a leading one. So that means that that's on the first and second column. So you come over here and look at the first and second column of this. And so a basis of the column space is just the set 2, 9, 3, 12. And 3, 9, 0, 9. And that's it. Now let's talk a little bit about why this works. When you do the reduced row echelon form, this over here is like a recipe that tells you how to get these columns by taking linear combinations of these. Like for instance, this last column would be to take 1 of the first and then subtract 1/3 of the second. So for instance, that would be take 2 minus 1/3 of 3 gives you 1. 9 minus 1/3 of 9 gives you 6. 3 minus 1/3 of 0 gives you 3. 12 minus a third of 9 gives you 9. And we can do the same thing for these as well. But the idea is the row reduction sifts out any of the linear combinations, and the leading ones tell you which things are linearly independent. So those are the things you have to keep, and the others you don't need. You don't need them for a basis. All right.